So in this video, it is an introduction about the power series. And let me write down a typical notation for the power series. So please look at the current summation of infinitely many terms, and you can see that each term actually carries out a term like x to the power n, you see? And informally speaking, you can really think of it as an infinite polynomials, right? So it's kind of like a polynomial, but it keeps going on and there's no stop. If you keep going on, there are actually infinitely many terms. So we can look at a concrete example from here. So please look at the current example. I give you something like 1 plus x squared plus x cubed and so forth. And the typical question here is that for what value of x does the power series converge? So let me put it here. So because it is the first time we see such kind of problems, you can actually check it one by one. For example, if you pick x equals 0, you can easily see what's happening to the power series when you look at the given power series. And because when x is 0, all the terms are actually 0, right? And basically it means the infinite sum is actually just the first non-zero term, which is the constant term 1. And of course, in that case, we can say it is a convergent power series when x is 0. And let's check out other values of x also. For example, if you put x equals 1. So I hope you can see what's happening now. If x is 1, I can put 1 to the power n as the term inside the summation. And essentially now you keep adding 1 for infinitely many times. And obviously, when you keep doing this process, the infinite sum is actually going to infinity, right? And in that case, of course, we can call it divergent, right? And this is a very simple example here. And I'm just giving you two different value of x to check whether the infinite series is convergent or not. As you can see, sometimes it is convergent and sometimes it is divergent. So you may be wondering, mathematically, if we have any systematic method for us to find all values of x for the power series to converge, because obviously it doesn't make sense for us now to keep checking the value of x one by one, right? And there are infinitely many values of x to check, and obviously we prefer a systematic method to solve it, and that's the main goal here. Let me put it here. The main problem is to find all the x such that a given power series is actually convergent. And without checking the value one by one, my advice is that you can actually try either ratio test or root test. And usually the ratio test is probably easier in terms of computation. So it is really my hint. And let's look at a concrete example to try it out. So please look at the current power series. If you are not familiar with the notations, we can actually expand it for a couple of terms. For example, basically the terms actually looks like this, and it keeps going forever. And of course, it is not that easy to see whether it is convergent or divergent if you are given certain value of x. And let's try a ratio test to see what's happening. By the ratio test, essentially it means you have to do this kind of calculation for the ratio here, and now you see our term an is actually the whole thing here. So let's put it in. The bottom is the fraction x to the power n divided by n, and while the top is the same term, but you need to replace n plus 1, right? So basically that's the fraction we have, and of course for the cancellation matter, we can actually flip the fraction in the bottom. So that's what you have currently, and you can try to cancel out some copies of x. You actually have n copies of x. So after the canceling, you're actually left with one copy of x at the top, and in that case, I can write the current fraction as n times x at the top, and for the denominator, you actually have n plus 1. And if you recall the ratio test, basically you have to do the limit calculation for limit n goes to infinity for the current fraction you have. And now please take a good look here. You see the x is essentially a unknown, which is a constant value that you don't know. I mean, x is a variable, but essentially you can really replace x by any values up here. So it means what? It means when you are taking the limit n goes to infinity, x does not depend on n, right? So it means that there's no relation between n goes to infinity and x. So basically, x is like a constant here. So basically, it means the important part for the limit calculation is for the terms that contains the n. And if you look at this limit, this one is actually the same as conceptually n over n. It is allowed because of the fact that when n goes to infinity, only the term with the highest power matters in the numerator and the denominator. So basically, the limit is 1 in this case. So let's come back to the equation in the purple color. Basically, after the limit calculation, it's basically the same as 1 times x now because of this one. And basically, it is the absolute value of x. And let's see what happens here. By the ratio test criterion, we understand that whether the power series is convergent or not depends on the absolute value of x. If it is less than 1 by the ratio test, we understand that the power series is actually convergent. And for the opposite case, when the absolute value of x is bigger than 1, we understand it is divergent. And the middle case is something we have to discuss further, but let's look at the current picture for now. So you see for the first statement, the fact that absolute value of x is less than 1 is equivalent to the inequality where x is actually between -1 and 1. They are the same inequality basically. So it basically means whenever the chosen x is actually between -1 and 1, if we try to present it in terms of the x-axis, we can actually make the shaded part in the purple color. For the value of x that are allowed to be chosen, then we understand that our series is convergent, right? And the third statement basically means we can cross out the values where absolute value of x is bigger than 1. And this fact basically means if you look at the number line, I use the cross to represent it. Basically, almost all the remaining values outside this interval -1 to 1 will give you a divergent series. So I should make it like this, is divergent series. But there's some uncertainty in this conclusion because of the second statement. You see, the second statement, the absolute value of x is equal to 1, basically means the following. Mathematically, if you solve it, it basically means x is either 1 or -1. And you can take a look at the number line that we have. We understand inside the interval -1 to 1, it must be a convergent power series. And these 2 points are exactly the boundary of these 2 points basically. So we have to check these 2 points basically. These are the boundary points. And so we understand this example is for illustration, but the fact is that in general, for any power series, it must satisfy such property in the sense that after you use the ratio test successfully, you always get an interval where all the power series is convergent if you are choosing an x inside the interval, and outside the interval is going to be divergent. And for the boundary point is something you don't know. It may be convergent, it may be divergent, and it's something you need to check now. So for example, this x is basically the right endpoint, right? And we have to check that. So let's replace x by 1 inside. Basically, you're getting this infinite series. And this one is the famous harmonic series. So if you recall, we can simply apply the p series test because the p as the fixed power is actually 1 inside the p series. And we understand that whenever the p is 1 or less, the infinite series is actually divergent, right? So basically, it means that the point here is actually divergent. So I'm using an empty dot to represent that we cannot include this point in our consideration for the values of x such that the power series is convergent. And for the left endpoint, I'm talking about this. So you can replace it inside the power series now. After the replacement, you're getting an infinite series like this. And please note that this term basically means an alternating series, right? It should be simple now because we can just apply the alternating series test. And there are 2 conditions to check. For the first condition, you have to check that the 1 over n, which is this term, for n goes to infinity, it actually converges to 0. And the fact is true because 1 over infinity conceptually is the same as 0. So the condition 1 is fine. And for the second condition, you have to check that the given term is actually a decreasing sequence. But I think it's actually obvious it is decreasing. I think it's obvious. So because both conditions are correct, we understand that at this point x equals -1. When we look at the corresponding infinite series here, it is actually a convergent series, right? So you see, if you look at the behavior at these 2 points, they are not the same behavior. So it means that if you look at the number line, we can use a full dot to represent this point because at this point it's actually a convergent series. And of course, as we mentioned before by the ratio test, we successfully tested that all the values between -1 and 1, we get all the points where the power series must be convergent. So we can make the following note here. So this is basically our answers to find all these values of x such that the power series is convergent, or you can use the interval notation to represent that. And I would like to add some definition based on our calculation here. So before looking at the definition, please look at some notes. For the first note, the fact is that this first example we just looked at is actually quite a good example for the general case in the sense that for almost all the power series you see when you use the ratio test, actually you can find that usually for the values of x to make the power series convergent, they are actually contained in one interval, right? And the fact is that on top of that, the boundary points give you some uncertainty, and you have to check the boundary points separately, just like what we did for the last cases, right? And now that's the first note. And the second note is the following. The second note is that you see for the meaning, the radius of convergence, um, you can imagine that the interval you have here is like a circle. If you imagine that it's actually a circle, so it means there's a center, and we can look at the corresponding radius, right? So essentially the radius is the length between the center and the boundary point along the circle here. So I'm talking about this length. I'm talking about this length. For example, if you have an interval like this, it is a center. I'm talking about this. So the radius is something like this, the radius of the circle, basically. If you imagine that it's actually a circle sitting on the x-axis. And for the interval of convergence, is essentially the values of x such that the power series is convergent. It means that it may or may not include the boundary points because it depends on your check on the boundary points. So let me write down the definition here. So basically, that's the end of this video.